Okay, Bismillah ar-Rahman ar-Rahim. Let's get started. Today we're going to talk about lecture 3 contents. We're going to basically review the, let me share the screen first just to be able to see everything. Okay, so basically I'm going to review what we talked about during the past 2 lectures about the identification of signal artifacts and their properties, and we're going to review what we did in the filter design experiments. Then we're going to talk about the differences between FIR and IIR filters in some details. We're going to talk about phase and group delay. We haven't talked about them yet. So basically we talked about the structure of FIR versus the structure of IIR. But this structure will have an impact on the phase and the group delay of that filter. We're going to actually explore the phase and the group delay and what they actually do in the output of the signal. Okay, so this will actually involve an observation here where we talk about, we observe that there will be a time shift in the filter output. So if you compare the signal before and after the filter, you will find that there is a time shift in the output. Okay, and this is actually related to this. They actually closely related to each other. So the kind of delay you're going to see here, or time shift, is related to the phase and the group delay. And basically you're going to talk about this relationship, and basically later we're going to propose or start using zero phase filters, which is a type of filters that doesn't have this kind of problems. So basically, if you want to have the same, basically the same timing of the signal in the input and the output, you have to use something called zero phase filters. We're going to talk about them and basically show some examples, and you will be very impressed actually when you see how it works. Then we're going to move to a whole new area, which is the Fourier domain filters. We talked about, or basically probably heard about, the Fourier transform, your signal and systems course. We're going to review the discrete Fourier transform of a signal. We just review the properties and how we do it and what comes out and things of that sort. And then we're going to discuss how to generate or design frequency domain filters. It's very easy to design a filter in the frequency domain, but we will see that there are some points that we have to be careful of and some drawbacks of using frequency domain filters. Do you have any questions about the contents or the previous lectures?
No, Doctor.
Okay. So now we're going to start talking about, this is the presentation that I gave you for this part. First of all, identifying signal artifacts. The first method that we talked about is the qualitative method. So basically, what we should do is just basically check whether the artifact signal has a lower or higher frequency than the actual signal. So basically, we want to check these, okay? Whether it's lower or higher. Okay, so in order for us to do that, we have to check one period of the original signal and the corresponding period from the artifact. Okay, so for example, if I look at the signal that looks like this, basically, this is the same thing that we have in the baseline wonder. This is basically one example. This is basically the period of the ECG. And basically, if you look at this here, if you consider this as a sinusoidal signal, okay, or a periodic signal, basically the period is the time between 2 valleys or between 2 peaks, okay? Just choose any of them, it doesn't matter, okay? There is a difference between the two, but actually it doesn't matter that much as far as the conceptual consideration of this problem, okay? So basically here, you see that the period here is very fast, but actually the period here, as you see, this is basically how long the period is here. Here, this is how long the period is in ECG. So definitely the ECG has higher frequency and the artifact has low frequency. And given that we have an artifact that is present in the low frequencies, we will need to have a high pass filter. Okay, So basically, we need to do something that would remove that low frequency and basically restore our ECG, or basically most of the information in the ECG back after filtering. Is that clear?
Okay, sir.
Please, whenever you have a question, just stop me, okay? I'm going to continue because actually it's difficult to ask you, given that you have to turn on the mic and then answer and then turn it off. So basically, whenever you have a question, just stop me and ask your question anytime, okay? So this is exactly what we did, and basically it was very crude, but actually gave us very good results, if you remember, okay? We designed this and we found that we have basically, if you remember, the period here is 4,000 to about 6,000 or 6,050, something like that. Say 2,500 samples, okay? Times a period, which is 1/36 hertz, 360 hertz. And basically, as we see here, if you look at the values here, basically, this is the period of the artifact signal, okay? And basically, you need to know the frequency of the artifact signal, which is 1/TA. You see here, this will be about 250/36. It's about, say, yeah, just get a very rough estimate. This is, say, about 8. So 36 or 2,500 over 3,600, it's about 8 almost. Okay, so basically the frequency is about 1/8, which is about 0.125. So basically hertz, of course. Okay, so basically if you design a filter with a cutoff frequency that is around that, is, for example, if it's 0.5 hertz, it should actually remove this artifact. And we saw that actually this was exactly the case. What you need to do from something like this is just get to a point that is close to what you want to do, okay? Basically, this is not exact, okay? You just want to get a rough estimate or an engineering estimate to start with, and then you're going to optimize that through experiments. So basically, you're going to get that value and basically design a filter and then try another one, just make it a little bit smaller, a little bit larger, so that you get to the optimal value by experimentation. But here, you just want to get a starting point. Point. Okay, basically filter design, starting point, okay? Because basically, if I tell you that the range of ECG signal, basically if you have a sampling period of 360, then the frequency of the ECG included will be from 0 to 180. So when do you start? You have to know exactly where to start. Okay, so in order for you to know where to start, you have to basically do something like what we did before, like this. Please remember that I'm not talking about new things. These are the things that we did last time. Same thing you're going to do also for basically if you have the EMG artifact. Okay, if you have muscle artifact, MA, the signal that has a label of MA, then basically you're going to have the same exact thing to do. You have to remember that you have to look at the artifact and basically try to estimate whether it has more frequency or higher frequency than the actual signal, or basically less. Okay, so basically here, if you see here, if you just take this part here and magnify it, you're going to find that it looks like this. So basically this definitely looks much higher frequency than this. So basically in this case, the frequency of the artifact looks much higher than the frequency of the ECG. And you can also do the same thing that we did, basically try to get the period between any two peaks and basically get an estimate. Basically based on the period, you get an estimate of the frequency, and then from the frequency, design filter, an initial filter. Then you optimize by experimentation around this estimate value. Okay, we're going to focus today on the baseline wonder artifact, and basically after the next lecture, which is going to be in 2 weeks, we're going to consider the EMG artifact and the basically the part about the motion artifact. Okay, this is exactly what I was saying. Basically, you want to get an engineering estimate. Basically, what you do here is just get the period here or the period here. It doesn't matter. You can also get the period from here to here. It's fine. It's going to be still the same. Okay, and basically you're going to get an estimate. It's not going to be the same. I'm talking about the same from the point of view of that you're going to get a close estimate to what you're supposed to be. Okay, and then you go to optimize after. Okay, so basically once you do that, you get the period, and basically the frequency estimate, the cutoff frequency estimate will be 1 over T. This is T. Okay, for the high frequency artifact, it's exactly the same. Just get the period between any two peaks here, and basically this will be T for the high frequency artifact. This is going to be very simple actually to do. It's extremely simple. Okay. For the filter design, what we did was to use a filter designer, as you saw before. Basically, you have to determine which type of filters. So basically, if we are going to do baseline wander, then you're going to choose this. Okay, and basically you have to put the frequency as 360 because this is the sampling frequency of the data that we have, and then put here the f-pass and f-stop. These are these 2 points. Usually, if I wanted a filter that removes 0.5 hertz, basically I want this to be removed. Any frequency below that must be removed. Okay. What I should do is probably put f-pass here as 1, and then f-stop as 0.5, and put here the attenuation I want, if you remember, okay? 80 means 1 over 10,000. Okay, this is usually very large, right? Okay? So basically you can change that. If you want to change the order of the filter, make the order of the filter a little bit smaller, you can make it like 60 decibel or even 40. Okay? Which is going to be 1 over 1,000 or 1 over 100. And basically, when you design the filter from here, you're going to get an order that you can optimize by changing these parameters. If you choose an FIR filter here, you're going to come up with an FIR filter. Usually, it has much larger order than IIR. But the IIR might not give you very good results in some cases. You have to really try all types of filters and then decide for yourself which one is best. Okay, I assume that all of you did that because actually we tried that in the first and second lectures. We did that on simulated data in the first lecture, and then in the second lecture we tried that with ECG contaminated with 60 hertz noise. We simulated that. And we tried that also on the baseline wander. Basically, after that, in order for us to be able to apply it to the filter, to our data, what we said is that it's better to actually generate the code for the filter so that you can basically, whenever you have the code, basically remove this first line, remove, so that it becomes a regular code. And then you can actually optimize by changing these values to whatever is more appropriate. So basically here I have f-stop as 0.1, f-pass as 1. I can change f-stop to 0.5 or 0.6, 0.4, whatever. I don't have to go back to the filter designer to generate the filter again. I can just optimize here. And then whenever I'm done, I basically use HD here. HD contains the filter. Okay, in a particular MATLAB format. It's not really an easy format to describe, but actually it has the filter. All you have to do is basically use the filter function with your HD that you designed and your signal. Basically, this is your signal. The signal with the artifact. And this is the filtered signal in the output. Okay? All this is just review of what we did before. Do you have any questions about it?
Clear, it's clear.
It's clear.
Okay. Now, talk about the FIR versus IIR responses, okay? We saw the magnitude response, and basically, we usually have really ridiculously large orders for the FIR filters versus ridiculously small orders for the IIR filters, okay? This is what we call the magnitude response. Basically, all the parameters that we entered are related to the magnitude response of the filter, meaning that at which frequency, which magnitude will be there. Okay, so basically this is the magnitude of the frequency response of the filter. Okay, so there is another side to that. What we see here is basically the phase. Basically all filters have magnitude and phase, and in the FIR filter case there is a big advantage in that the phase is linear. Okay, the phase is linear. We'll see in a second why the linear phase would be actually advantageous. And here it's nonlinear. Basically, imagine that the linear phase, because it's whenever you look at the FIR, if you remember, we have h of s or h of z for FIR. It's just a collection of a naught plus a1 z minus 1 plus just a first order, basically a polynomial of z. Here it's a little bit complicated. It has a polynomial numerator, basically e0 plus a1 z minus 1 and over 1 plus b1 z minus 1 plus b2 z minus 2 and so on. Okay, so basically you have here a rational function. Basically you have a numerator over a denominator. So imagine that each one of z actually by definition is e to the j omega, and this is omega. Okay, so basically this is a complex number. When you add them together here, you can actually imagine that you're going to end up with something that would look, it still has the form of e to the j omega. If you look at the phase here, if you remember the Euler identity, basically maybe I should go to the other side here and just explain it a little bit better. Okay, I still have to talk about this later. Maybe I will talk about it here. If you have a number that looks like this, 5 e to the minus j omega. Okay, basically this is a number. This is a complex number. Okay, from the Euler identity, basically this is the magnitude e to the j phase. Basically, this is the format for a complex number. So whatever is multiplied by e to the j is basically the magnitude. And whatever is multiplying the j here is the phase. So basically m here is equal to 5. And the phase here is equal to what? Can you tell me? Minus omega. Minus omega. It's not omega. It's minus omega. Okay, so basically this is actually, if you try to draw the phase versus omega, it's going to be a linear curve, and basically because it's negative, it's going to look something like this, maybe something that looks like this, linear curve that looks like this. Okay, the slope here is omega. Okay, this is the phase. Basically, whenever you have terms that look like this, it's very easy actually to see that you're going to end up with a linear curve like this. Okay, if you imagine that you have something that looks like this, x is equal to 5 e to the j omega plus 6 e to the j twice omega over 1 plus e to the j omega. Okay, if you try to put this as m e to the j omega, or j phi, you're going to find that basically this phi here is not going to be a linear function of omega, not alpha omega. Okay, it's not going to be like a linear function of omega. Okay, it's going to be much more complicated than that. Imagine that you have, if you want to basically take this and basically convert it into m e to the j phi, you can find out that it's very difficult to combine that. You have to basically use Euler identity to put that as r plus j I, basically real plus j imaginary, and this is the same, and then reconstitute it again and basically do the same here and basically try to get the phi and the m from whatever you're gonna get. So basically whenever you have a function that looks like this, you have a numerator and the denominator that is not 1, you're going to end up with a nonlinear phase. The problem with a linear phase is that if you remember from the things that we talked about before, or you may have heard about before, basically if you have a sinusoidal signal, if you want to write a sinusoidal signal in terms of magnitude and phase, or frequency and phase, remember that we have sine omega t plus phi. Okay, this is basically the frequency. This is basically the phase. Remember that? Okay, so basically the problem is with the phase is that if it's a linear phase, meaning that this phi is equal to, for example, omega t. If it's a linear phase, it's going to be basically the phase times a constant. Okay, and basically, it changes with a constant t, for example. Okay, so basically, if you have something that looks like, if you have a sinusoidal signal that looks like this, omega t minus t naught. Okay, this will be basically like omega t, sine omega t minus omega t naught. Okay, so basically, if you can make your signal look like this, then you will see that that phase is related to the frequency by omega. Basically, the phase itself, phi, is equal to omega t naught. So this t naught is the delay, and this is the phase. Meaning that whenever you have a phase, you're going to end up having a delay that corresponds to the relationship between the phase and the delay is omega. So we can come up with an equation that will tell you that whenever you have a delay, whenever you have a phase, or basically the delay is equal to partial phase, partial frequency. Okay, so basically if I take partial phi, partial omega, this will be basically the delay of the signal. Okay, and the delay is very important. Let me show you why. You go back to this curve here. Here it's linear, meaning that if you take the derivative with respect to omega, it's going to be constant. Here, if you try to take the derivative with respect to omega, here it's going to have a different value from here. So for example, here in this part, this will be very steep. Okay, this here is going to be very flat. So basically here is going to be small, you're going to have small value, and here you're going to have a large value if you take the slope. Okay, and meaning that here you're going to have large delay. Here you're going to have a small delay. This is a problem because basically now your signal coming in, if you have a signal that is in the first part of the frequency domain, like below 10 hertz or something like that, it's going to experience a much larger delay than a signal in the 100 hertz. If you have a signal, any signal in the world, basically any signal anywhere, is just a composition of a summation of some of frequencies, but just a summation of different frequencies, and basically this summation is basically each one of the components has a different delay. If you enter this signal into a filter, and this filter causes changes to the delay, the relative delay between the components of the signal, you might end up having a distortion in your signal. Okay, so basically a nonlinear delay will be a bad thing. Let us go back and basically talk about this a little bit more. So basically, the group delay is basically the derivative of phi with respect to omega. And since we're talking about delay, we actually put a negative sign here, so that we emphasize that it's a delay. Okay, it's negative time. Okay, if you basically take the same exact curves here for the phase, and here the phase, and take the derivative, it will look like this here, just a constant in the FIR filter, And basically here it's going to look like something that is not really very flat, which is a problem actually. Because here, as you see here, you're going to have frequencies that are in this range having delays that are maybe 200 samples. So basically, if you have a sample coming in, it's going to be delayed by 200 samples at the output if the frequency is below 10 hertz. While if you have 100, it's going to be almost zero. Okay, so this is the problem. Okay, let's try that in MATLAB to see it for yourself. You can actually see that for yourself in MATLAB. We can design a filter and see that for ourselves. You can actually see the phase and the group delay yourself on MATLAB in the filter designer. So basically, you're going to just enter the same parameters that we saw last time. Maybe you can talk about the filter that we use for the 60 hertz, so that it can be clear to us. So 50, and the f-stop is 59, okay? And a-stop, gonna make it 60. That's arbitrary, it's no particular reason. So basically, let's look at something that, an FIR filter first, and then we're gonna look at, at the IIR filter as well. So can I design the filter? Looks okay. 79 is not bad. Above here, you're gonna see different things. Basically, this is actually the magnitude response. This is the phase response, which is what we saw. This is basically the magnitude and phase together. And here, as you see, minus d phi by d omega is basically the group delay. Okay, so let's see each one by itself. So basically, this is the phase. Okay. By the way, this is just basically this is the low pass part. Okay, this is the most important part basically, because after 60, it's just going to be multiplied by almost a very small number. So basically, the phase doesn't matter. Here, the phase is linear. Let's look at the d phi by d omega, just constant. And the delay is basically, you can notice that it's about 39.5, which is exactly n over 2, the order over 2. So whenever you have a filter, that an FIR filter in particular, that has an order n, okay, the signal at the output will be basically delayed by n over 2. Okay, and this can be actually explained very easily. Okay, maybe I can go back to here and just explain it to you. I'm going to talk about this later, but let me just talk about this other thing first. Basically, if you have a signal, just let's assume that we have a signal that starts from here and basically extends all the way to here. And as we said last time, what's going to happen is that we're going to have a filter that basically apply that filter in terms of convolution. So basically, the filter, say, is going to have 4 points, start from here to here. This is the center point of the filter, and basically, just say that this is 0, this is -1, this is -2, this is +1, this is +2. Okay, and this is a signal here. You're going to have the same exact signal. This is signal number 1, 2, 1, 2, 3, 4, and so on. Okay. Basically, as we said last time, you take the filter and basically flip it and basically keep shifting until basically you get inside, and each time you multiply, add, and basically compute the point. So here I would multiply. This is going to be as if it's 0, and this is as if it's 0. So let's draw some signal here, and basically you have a point here. You have a point here. You have a point here, and so on. Here you have also maybe the filter is simple like this, basically. Okay. So basically your filter looks like this. Okay. So basically maybe another one here. Okay. So basically, the filter will be multiplied by these points. So basically this point here will be multiplied by this point, 0, and this is 0, and this will be multiplied by 0, and this will be multiplied by the first point, this here, and just add them together. Okay, so whatever I get from here will be added to the what I get from here plus what I get from here, and this will be the result. This result will correspond to the first point in your output. This will be the output at point 0. Okay, this is the first point that you're gonna get. Okay, and so on. The thing is, you have to notice that in order for me, if I want to compute this point here at 0, I have to have what? I have to have the point at 1 and at 2. So I cannot produce the output for 0 until the point number 2 is already with me. So I have to wait this time to get output for 0. You understand that? I have to wait until I have enough points here to basically match half of the filter in order for me to be able to compute whatever I need for point number 0. So basically, whenever I have a signal, if this is a FIR filter, usually FIR or IIR, by the way, S of t, basically if this has a length of n, then what you're gonna have, this actually has to be of n also, so that it's, what you're gonna have is S dash, the filtered version of S, of n minus n over 2. You're not gonna be able to get rid of that delay. And basically, you're going to see that ourselves. Maybe you can just try that and see from one of the codes that we used last time and see that delay for ourselves. Basically, let me try. This is the last one that we did last time. Okay, this is the last one. This is the filter, the output that we got last time. This is one of the codes that I posted for you last time. This is the input, this is the output, this is the input. The input is the noisy signal, this is the output, and this is the ideal. Let's take, for example, the points around 4,000. Maybe we'll take the point around 7,000 because actually this looks a little bit unique. Okay, so let's zoom in on that, around 7,000. It looks like this. Okay, this is 720. Let's do the same thing here. Actually, first of all, you notice that, maybe you can go back. You notice that this part here looks exactly like this part here and this part here. So basically, this part here was delayed until here. Okay, can you see that? So you have a delay of about what? You see here, it's about 6,000, maybe 200, something like that. And here it's 7,200. Let's look at order, the filter order. I'm not sure here the order. The order here is n, maybe you can just print it. And it's about 1790. If you take half of that, it's going to be about maybe 900, something like that, because it's almost 1800. So actually, the delay we see here is about 900 points. It's actually very close to being that. Maybe I can magnify it a little bit. Magnify this a little bit. Sorry. See here? Basically, let's magnify it a little bit more. If you look at this here, this point here is the x is about 6142. Here, look at the x here, 6141. Here, it's exactly the same point in the output, 7038. So 7038 minus 6141 is going to be around that 900 that we were talking about. Okay, so basically this is a delay that is coming from the order of the filter. Okay, so whenever we apply a filter, we expect a delay that looks like this. It's never going to be exactly the same. Is that clear? This is very important for you to understand. Is that clear?
Doctor, I have a question, please.
Go ahead.
Could you please make this the filtered signal smaller, smallest thing?
The signal is smaller, the filter?
Yeah, I mean, yeah.
Actually, it shouldn't.
Make it.
It shouldn't.
Because the beginning, I see it's delay like 900 also from the beginning when the signal starts.
I'm not sure I understand. Can you you talk about the magnitude or the delay?
Can you zoom it out? Not in,
okay.
Out.
This one here?
Yeah. No, out. Zoom it out. Not in. I don't want it to be bigger. Smaller, please.
Okay.
Yeah, more.
Okay.
More, please.
Okay.
Yeah, see on left when we start the signal.
Yes.
Here. Seems like 900 also delay.
Yes, this is actually the transient. This is a transient. Okay, because actually, as we described last time, because of the filter starts at 0. Okay, starts at 0 here. This is at 0. Basically, you have to wait until every part, like this part here, becomes at 0, so that all the points in the filter are multiplied by actual points in the signal. Before that, a part of the filter will be multiplied by zeros, which is not really correct. So basically, this is another thing. This is actually basically one of the other things that we should take care of. So this n over 2, the order over 2, applies for the transient at the beginning and the delay of the output signal after the transient is over, that the delay between the output signal and the input signal.
Yeah, clear now.
Okay?
Yes, okay.
Okay, so let's go back to Filter Designer. So basically, see here, this is very flat. So basically, this is the delay that you're going to expect from the FIR filter. Again, this is a magnitude, this is a phase, and whenever you take the basically the derivative of the phase minus the derivative of the phase, you're going to get a value here that will be the delay of the output signal relative to the input signal. This is for the FIR. It's very flat. It's very nice, meaning that if you have a summation of two frequencies, and the first frequency has a phase of 0 and the other one has a phase of 60 degrees, for example, the relationship between the two frequencies at the input will remain the same at the output, because basically the delay will basically delay all the frequencies by the same amount. Let's look at the IIR filters. Okay. And basically, let's try, for example, whatever, any type. Okay, and it's exactly the same specifications, and just design a filter. Okay, this is a filter. Looks very nice, actually. It's very flat here. It's very, it's basically goes below the 60 decibels that we wanted at the point right before the point we wanted to cut off. It's fine. It looks fine. Let's look at the phase. The phase looks a mess. Basically look at the important part that is in the pass band. The part in the stop band doesn't really matter that much, because basically it's going to be multiplied by a very small value. So basically the most important part of the phase is the part in the pass band. If you look at the phase, if you look at the group delay, it's going to look like this. Basically imagine that you have a frequency here near DC, and another frequency at, say, 50 hertz. 50 hertz should be actually in the pass band. So basically, it's going to be delayed by 35 samples, while your sample or your signal at near DC is going to be basically delayed by only 5. This is going to be a problem, because what you're going to do is that you might end up having something called harmonic distortion, meaning that the frequency content of your signal, basically, instead of being exactly matched each other, exactly the same way they are in the input signal, they might change a little bit. If you're adding multiple signals, which is actually most of the signals that we see are basically addition of multiple signals, okay, multiple sinusoidal signals at least, okay. So basically, what's going to happen is that this variation in the group delay between different frequencies might cause some distortion at the output. Would that mismatch in the group delay cause a distortion, or basically should I just dismiss the IIR filters because of that? Actually, you shouldn't. What you should do is just be careful about this. Okay, some applications might actually have frequencies that are far apart, and if you have different group delays for each, you're going to have a problem. In some cases, maybe you're going to see that in ECG. Some cases it doesn't really matter. Most of the frequencies are close to each other. Maybe it's in this range, and basically the difference in group delay might not really matter that much. So what you should do is basically use the IIR filter and basically try to see the output, whether it has some additional artifacts that were in there before or not. Okay, but you should just be careful about basically this group delay issue. Okay, so in IIR, any IIR type of filter, you're going to have a group delay that looks like this. If you have an FIR, it's going to look flat, and basically it's definitely in the advantage of FIR filters, but as we saw before, FIR has a really bad disadvantage in that the order of the filters produced by FIR filters are much higher than those produced by the IIR filters. So now you have an engineering trade-off. You basically have an advantage in one filter with a disadvantage. And basically, you weigh the two. You basically balance the two according to a particular problem. So in each problem, you will find that whether this balance can be maintained or not, basically. Okay? So whether you use a very small order with some distortion in the group delay or in the phase, or you use a much larger order and basically don't have any problem with the group delay. So basically, this is one of the things that you should experiment with in each problem that you're going to work on. Okay? Okay, now we're going to talk about a different type of filter. There's a very unique filter that doesn't have any phase. Okay, so basically, we're just talking about phase and basically saying that this phase basically is the one that is causing the group delay. If I have a phase of 0, what's going to happen? If the phase everywhere is 0, will there be group delay? Basically, the group delay is the derivative of the phase with respect to omega. If it's flat at 0, then the group delay will also be flat at 0 because derivative of 0 will be always 0. Okay, so basically this is the type of filter that I was actually having here. I just got the picture because actually it's very clear. This is called basically a zero phase filter, and it has a very nice idea actually. Just imagine that you have your original signal here. This is the original signal, x of z. Basically it's x of n, but actually let's consider everything in the z domain so that it becomes a little bit clearer. Okay. Basically, after the filtration, it's going to be x of z times h of z. Basically, it's the same as h of n convolved with h of n. Okay? What you do here is the key to what happens next. So if you do something called time reversal meaning that if I have, basically, let me draw a sample signal. Basically, if you have signal here, okay, and basically this is signal. 1, 2, 3. Okay, this is at 0, 0, 1, 2. After the time reversal, it's going to look exactly the opposite. So basically, you're going to have a signal that looks like this after the time reversal. Okay, so basically, just I reverse the time. So basically, this is the end point. Basically, the end becomes here, becomes first, and the first becomes last. Just time reversal. If you remember that the z minus 1 was a delay by 1. If I reverse the signal, basically, if I have a signal that is, for example, x of z, the time reversed version of it is x of z minus 1. Okay, so basically just basically replace each with z minus 1. When you do that, basically the output here is going to be, instead of having an output of x of z times h of z, basically you're going to replace it by z minus 1 here and z minus 1 here. Okay, so basically when you do that, basically you're going to end up, if you filter it again with the same exact filter, it's going to look like this: h of z minus 1 times h of z minus 1 times h of z. Basically, since you have here z minus 1 and z, basically this will be basically h of z times h of z minus 1 is going to be basically h of z magnitude square. Okay, magnitude square meaning that basically you're not going to have any phase at all. Remember that z is equal to e to the j omega. Okay, so basically if you have the absolute value of h of z, this will be basically a real number. So when you do that, this part here will be a real number. If you do another time reversal, basically this is a real number, it's not going to matter. Basically h of z minus 1 times h of z is going to be exactly the same as h of z times h of z minus 1. It's a real number. This is basically the same. This is also a real number. The x of z returns back to basically the same format that you had here. Okay, but now the filtration, instead of being multiplied by a transfer function that is just h of z, is going to be h of z absolute value square, meaning that it doesn't have any phase at all. When you have something that looks like this, first of all, you're not going to have any transient, because basically you don't have any delay. The second thing is you're not going to have any delay in the middle, basically. That the signal will be exactly in phase with the input signal. The thing why people thought about this, basically the original idea was that basically if you look at something like this, basically, this is the input signal, this is the output signal. The transient happens only at the beginning here. At the end, you don't have any transient. It looks very nice. If I reverse this signal, if I basically time reverses, so basically this is the starting point and this is the end point, you're going to be able to compute, basically the transient will be in the part that has the last points in the signal. And the first points in the signal will not have any artifact. We're not going to have any transient. So basically, if you do it like this, you can actually imagine that you can get the first part here from the time traverse signal and the last part here from the regular signal. And basically combining them together, it's going to give you something that actually doesn't have any transient and doesn't have any delay compared to the actual signal that you have, that you started with, the input signal. Okay, and I know that this might be a little bit theoretical for you, but actually let us try it first, and then, so basically this is the same code that we generated the signal with, this output with. In order for you to apply the zero phase filter, MATLAB has a very simple function that does that. Instead of using here filter, you have to use something called filt. That's the same thing exactly, okay? So basically, let's go back and look at the help for filt. Basically, it's a zero phase forward and reverse digital IIR filtering. Basically, it can be IIR based general form is IIR, but you have to have here the components of the IIR filter, the numerator and denominator. Okay, we remember that we talked about the IIR filter. Basically, it has a shape, or it has a transfer function that looks like basically h of z is equal to a naught plus a1 z minus 1 plus over 1 plus b1 z minus 1 plus, okay, this is called b of z and this is called a of z. Okay, and basically the b, sorry, I'm supposed to have exactly the opposite one, sorry. It's a here and b up there. Okay, this is a convention MATLAB uses. So, okay, so basically the b of z is basically just the coefficients here. b0, b1, b2, and so on. If you have b0, it's multiplied by z to the power 0. b1 is multiplied by z to the minus 1, and b2 minus 2, and so on. The same thing here for a. So basically what we got from the filter design function was hd. It's actually in a format, special format for MATLAB. It doesn't really have b of z and a of z. There is a conversion function called transfer function that takes h of hd and gives you b and a. Okay, let's try that. I'm going to go back to MATLAB and try that. So basically, I can go back here to the editor, and basically whatever I get here, I'll just say B and A is equal to TF, it's transfer function of HD. I think it looks like this. Yes, I think it should be. Yes, I think it should. TF. Okay, filter, yes, B and A is equal to that. Okay, so here instead of using filter, here instead of HD, I'm going to use the B and A that I got from here. Basically, this is obtaining the transfer function as B of Z over A of Z. And then I'm going to use that here as filt. Okay, this is exactly the same code. I'm basically just going to run it like this and see how the output looks like. How do you like that? First of all, we don't have any transient here. We don't have any transient at the end. Everything looks matched. Want to make sure if it's matched or not. Let's try that again. Maybe we can draw them on top of each other. So I'm going to go back here, generate another figure. And I'm going to plot first signal, the sig-x. I think the sig-x is the actual signal, the problematic signal. And then in order for you to draw something else on top of this, I'm going to have hold on and plot the other signal, the filtered signal, with a color of red, just to be able to see them. Should be like this, and then hold off. Whenever you do hold on, basically whatever you try to plot again is going to plot it basically on top of whatever is on the string. If you don't have hold on, it's going to basically override the existing figure. Let's try that. This is figure. Okay, there's a problem here. Basically, what you see here is that this doesn't have the same level, right? Did you do anything to the signal? On to the range. Actually, it doesn't have the same level for some reason. Oh, okay. Actually, it's first of all, if you look at the figure here, it's basically yeah, actually it's very difficult to see them on top of each other. One key aspect that controls the magnitude of the output signal is basically the f-pass. The f-pass parameter here. Basically, we chose that, or we changed that to 0.5, which is really large. Okay, so not f-pass. The should be the ripples actually. Equiripple.
Doctor, in figure 2, you want to compare between the original signal and after filtering, or what?
No, actually, this is the filtered, and this is the origin. This is the artifact signal.
Yeah, the signal. No, okay.
But the point is, the level is different.
I thought you mean the signal and the output signal.
No, actually, no. This is the output signal here. This is the output signal, and this is the input signal.
Input signal,
Okay.
then upload signal.
The what? See here, I actually plotted the sig-f. Sig-f is the filtered signal. And sig-x is the signal with the baseline wander artifact. Okay, the problem I see here is that basically this is a high-pass filter. So actually what happened is that it removed the DC value. Basically the average of the signal is the DC value. Okay, so whenever it removed the DC value, basically the signal came out with a center, basically it's centered around 0. Okay, so if I wanted to have the same exact signal level that I had before, like basically this is around 800, what I should do is probably compute the average here and then add it to the signal here. Do you know what I mean? This signal has a DC value because basically it's all positive numbers, and basically if you compute the average is the DC value of the signal. So basically the average of the signal here will be something like 800, something like that. Okay, when we basically pass this signal through a high pass filter, the DC is basically frequency 0. So it's going to be removed with the other frequencies that were removed. Okay, if you don't want to do that, what we can do is probably just compute here. Let's just compute the DC is equal to mean of sig-x. And then here for the filters, I'm going to add that. Okay. Basically, I'm trying to preserve the DC value or the initial DC that was added to the signal. Okay, that was present in the signal. Basically, this is the original DC offset. Okay, here, 0 phase filter plus preserve DC offset. Okay, so I took it from here and added that here. So let's try it and see what I mean. See now what I mean? Basically, they came out overlapped. Let us look at, basically this part here is very clear. Basically, you have here DC offset, you have here the baseline wander, here it's not. I'm going to zoom in so that we can see that actually the peaks are exactly aligned. See now? Perfectly aligned. Here, the difference here started here very small, and then became large, and then became small again, because we saw the difference because of the baseline wander. So the signal in blue represents the basically the original signal with the artifact, where basically the signal was actually moving around, basically going up and down. Here, the signal output look exactly the way we want it. It doesn't have any DC or that doesn't have any baseline wander. White exactly, basically it's aligned exactly with the original signal. It doesn't have any problems, doesn't have any delay, anything like that. In order for me to show it to you a little bit more, what I'm going to do is have another signal. Just put F2 here. I'm going to use filters. Okay. You also use filter with B and A, and I'm going to have another figure. figure 3. I'm going to draw SIG-X and SIG-F2. This is the one that had, basically the one that is using filter, just filters, doesn't have the zero phase filter. Let's see the difference between the two. This is basically the one that we were seeing, talking about. Basically, this is the one that basically came out of filter. Let's basically zoom in on exactly the same part that we were observing in the other one. See now the delay between the peaks? They are not aligned. Compare this to this. Very clear. Okay. Okay. You see here, basically, you have very clear distinction between the two peaks. There is a time delay between them. Okay, and basically here you don't really see any delay at all. So the use of filter, as you see here, gives you something that is really clean. Basically looks very nice from the beginning and the end of the signal. See, even that part, the small part here is still present here, exactly the same. Perfectly aligned. Okay, so the use of zero phase filter is very good actually. It gives you something that doesn't have any transient, it doesn't have any group delay basically during the signal. What is the disadvantage of using zero phase filter in your opinion? Can you give me your just try to guess and let me know what you think. Why shouldn't we just use zero phase filtering for everything? Looks perfect. Give a signal that doesn't, basically the other one doesn't have anything any close to that. Okay, first of all, in order for us to compute the filter, we basically had to do something called, the thing that we just talked about. We had to do basically time reversal. Time reversal meaning that you have the last point and you made it to be the first point. You take the last point, you started from the opposite side of the signal and basically started from there. This means that you have to have your whole signal in order for you to be able to filter any part of it. Imagine that you have an application in ECG, you want to design a digital filter that would work online in real time. As the ECG signal is coming, you're filtering the signal and producing real-time output. Okay? Can you do that with zero phase filters? You cannot. So zero phase filters are very useful when you're doing something like offline. You're basically, you have your own signal, you have the signal ready, you have the signal somewhere on a computer, you don't have any hurry, you have all the, basically you have all the points of the signal, and then you can do the zero phase filtering on the signal using the zero phase filter. If you have something that basically like a real-time data acquisition system, something like that, like an ECG system, and you'd like to implement a filter that would actually process the data as they come in and produce the output to be displayed, you cannot do that with zero phase filters. Okay? Is that clear? Is that the idea clear?
Yes, yes.
Okay. So basically, it's very important. So basically, the difference, let me write that down. So basically, zero phase basically offers zero transient and zero group delay. Cons cannot be used for real-time processing. okay? Because you need the whole signal at the start of processing. Okay, you cannot have basically points coming in and you process them and display them. You cannot do that with zero phase filtering. But it's very nice if you have, for example, some people collect data from patients and then they do that, they just put them in a database, and some other people just take the data from this database and they want to process them to detect a few conditions from the patients. Then in this case, the processing system can start with some filtration based on zero phase filtering, and then basically start processing or basically detecting the conditions after the artifacts are removed. But if you're talking about implementing that in hardware or for signals that are still coming in, you cannot do that. Is it very clear? Okay. I want to try that also, and I just basically give you some more examples of that. Let's just look at figure 2. Figure 2 looks okay. Let's try that for the code that we had for the 60 Hertz, because actually I wanted to show you something that is interesting in that. Okay, I already have that here. I added that to this is exactly the same code. I added this filtration, added the filt in the code of last time, and let us see what happens here. So basically, see how it looks like? Looks very nice. I want to show you something before that. Let me just close all the figures. In the filter design, if you remember, basically we have the D-pass, the basically the passband ripple, we had it like 0.1, something like that, okay? Let's try that here. Let's try it like that and see what happens, how the output looks like. How do you like that? Does this look good? Looks a little bit different, right? The output of the filt looks a little bit depressed. It has a little bit of a difference between the values of the actual signal and the basically the output is a little bit different. Here, when we have a passband ripple that is a little bit large, basically you're going to end up having something that looks like this, which is not good. Okay, so in order for you to make it a little bit smaller, let's just put a 0 here, for example. Try it again. It's a little bit better. Let's try it here as 0.00. This is almost perfect. Okay, so the passband ripple, even though it didn't really matter that much, you're talking here about maybe basically variations in the order of very small. Basically, it's plus minus this number. Okay, so basically you're assuming or basically trying to constrain the filter response to have the passband almost perfectly linear, basically almost constant everywhere with very small variations. These small variations actually will cause the output of the filter to change a little bit. So even though it might not really appear that like much, basically, this is basically what I have here. Basically, this is the filt, and this is the filtered, the regular filtration. Actually, this looks almost perfect like this, but actually there is a small difference in the magnitude. Let me return it again to whatever we started with. Here, if you look at this and this, the first one here is the original, and this one using filt. They look perfectly, look okay, look very nice, they look exactly the same, but actually there's a difference in level between these two. Here, definitely the transient part here is definitely very pronounced, but actually if you look at the figure here, you will notice directly that you have a problem here. This is, I'm sorry, this is the actual, this is a filtered, and this is the one that is using filt. There's a difference in level, and this difference in level is related to the passband ripple. So this is the first time we see that the passband ripple basically has an effect. So in order for you to be able to get something that is as close as possible to perfect, has the same level as the original signal, you have to have a very small tolerance for the passband ripple. The reason I wanted to have something that looks like this, rather than the one that we just saw, is that basically what we need to do is basically want to have a quantitative comparison of the signals. Want to basically look at the difference between the input and the output. I want to take the difference between the two signals, like what we did before in the ECG demo. Basically, the one that we did before in the ECG demo, where we have the difference between the two signals. Like here, for example, we took the difference between the original and the artifact signal. We came up with something that looked like this. If you have a delay, if you have a shift in either magnitude or phase between the two signals, you're not going to come up with something that looks like this. It's going to basically have another component that doesn't have anything to do with the artifact. Okay, so you have to have perfect alignment in time and perfect alignment in magnitude in order for you to be able to basically subtract the two signals and basically base a decision based on that. So if you want to have quantitative comparison, what you should do is basically you have the estimate or the filtered signal minus the ideal signal. If you have, for example, the reference signal that you have, that exactly what you have here, you're given the true signal and you're given the filtered signal. You want to subtract the two so that you can estimate whether the signal that you filtered is good enough or close enough to your original signal or not. If you subtract the two signals, you can come up with another signal. But actually, I want to compare them with just one number. So what I do is basically square that or get the root mean square value of the difference. So I basically have the average here, the mean of the square, and then basically get the square root of that. Okay, so this gives me the error in terms of root mean square value, and this is actually can be very good indication whether the signal is a good approximation to the original signal or it has a problem. Okay, so basically you need to use filter or zero phase filtering in order for you to do that. Is that clear? Let's leave the part about the quantitative comparison till the end after we finish the other two types of artifacts, because actually it has some more details, some more delicate points that we have to actually emphasize, particularly because basically if you look at the signals here, I'm not sure, actually here I plotted only 1,000 points, but sometimes you will notice that the filtered signal might be actually better than the true signal, okay? And in this case, there might be a difference, and this difference might cause this root mean square value to be a little bit different. But let's leave that till a little bit later. This is a part about the group delay, basically, correction. And basically what we said that is basically whenever you have the original signal and the output of the filter, if you try to subtract them, you're going to get something that looks like this. Doesn't have anything to do with, basically has so many different components because basically these are not aligned. So parts of the ECG here, the peak, the QRS, for example, will align with the P, for example, here. So when you subtract them, the QRS will still remain here. And you're going to come up with something that is incorrect. If you use the filter and have a zero group delay, then when you subtract, you're going to get something that looks like this, okay, which is actually correct. So that you can actually rely on, if you compute the power of this, or the root mean square error, basically of the difference between these two signals, is going to be actually relevant to what you're looking for. It's going to be an indication to whether you are close to the the output is close enough to what is required or not. Okay, so basically that's why we actually, if you want to try a particular filter and test whether it produces the best output or not, basically, or you have multiple filters, you want to compare their output, the best way is to you basically just use filter and subtract and then compute the root mean square error. This, of course, is related to the zero phase filtering that we talked about. And basically, this will basically remove the first part here, the transient part, and basically remove the delay that you encounter between the input and the output of the filter. One additional advantage, it's not really what we meant to have, but actually the filter order after filter is going to be double the order of the original filter. Remember that the filter that actually ended up being used in the zero phase filter was h square, h of z times h of z minus 1. Basically, these two will basically have, it's like h of z. So basically, if you have a certain order for h of z, it's going to be double when you multiply by h of z minus 1, which means that the processing will be doubled. Okay, so this is another side of using filter for filtration. Okay, so basically this is an example. This is basically one of the examples that we just did. Basically, this is what we did last time, actually at the end of last lecture, where basically we estimated the artifact frequency, and basically we saw that this is a low pass artifact, and we removed it using a high pass filter, and we used it as FIR. You can actually try it as IIR as well. So basically, we're not going to talk about the EMG or the motion artifact. I actually wanted to talk to you about another type of filter, which is basically the frequency domain filters. When we take the actual signal and go to the frequency domain and basically process that in the frequency domain instead of the time domain. Okay, the idea behind that is actually much simpler than any of the other filter types. So basically, if I talk about frequency domain filters, just imagine that you have a signal that looks like this. Okay. If you take a frequency domain or take the Fourier transformation of that signal, you're going to come up with a spectrum, whatever a spectrum looks like. Sorry, I wanted to have something that looks symmetric, because usually, okay, almost. So if you have a real signal here, you're going to end up with a symmetric signal here, spectrum. So this is frequency, and this is magnitude, for example. So basically, if this is x of t, it's going to be x of omega, for example. Okay. The point is, if I have a particular artifact here, if I have, for example, like exactly what we did before, if I wanted to remove the frequencies between 0 and 0.5 hertz, would it be easy or easier to just pick that out from here? Basically, if I go back to this part here, and basically because actually frequency domain should be symmetric. So if I take this part here between minus 0.5 and plus 0.5 and basically remove it by hand, just make it 0 by hand, wouldn't that be a filter? Can you answer me just by intuition? If I just manually go to the signal spectrum, I remove them and basically do another, basically take that and basically have the inverse Fourier transformation, okay, and got back a filtered signal. Wouldn't that constitute a filter? Wouldn't that work? And wouldn't that be an ideal filter? Because basically it's exactly like what I want. The filter here looks basically it's as almost as an ideal filter like this. Basically, it's going to look like this. So this is 0. And this is minus 0.5. This is plus 0.5. And this is basically brick wall. Okay, it's basically minus 0.5 minus epsilon is going to be 1. Minus 0.5 plus epsilon is going to be 0. The response will be exactly 0. It's not going to be attenuated by 1 over 100, for example, or 0.01 or whatever. No, it's going to be 0, 0. Just basically 0. Okay? The same thing here. So you have very sharp transition band here. Okay? So is there any problem with this concept? Can we do that? Or there might be some problems in doing that. Can you see any flaw in that concept or in that principle?
I think this is like stop band filter.
What?
It's like stop band filter.
Yeah, it's fine. But actually, you can do whatever you want, actually. So basically, if you wanted to do the reverse way, basically, if you want to have a low-pass filter, you can basically keep only the frequencies below a certain value and remove the others. Remove them, making them 0, basically. Just put them as zeros. Would that be okay? Actually, it should be okay. It should be in principle, it should be okay, because basically, you're doing exactly what the filter should do. You have a frequency selective filter. It has different response to each frequency. So here you actually do it as an ideal filter. Instead of implementing that in the time domain, you're implementing that in the frequency domain and basically doing that as an ideal filter. The point here, you can do it, of course, but there are some a little bit tricky topics here. But actually, it's, in principle, you can do it. But the main problem that you might have is that it's going to be like the filters. It's going to have a problem that you have to have the whole signal before you start. And you have to apply a Fourier transformation. The Fourier transformation is an expensive operation. Okay, so basically, it's not practical to use it for online processing, okay? But actually for offline, if you have the signal already and you have a good computer, things of that sort, you're not in a hurry to produce the output, then this is your filter. If you want to do something that would actually be implemented in a microprocessor or something like that, that receives signals, receives samples, not signals, samples, and processes them and outputs them for display, then this is not going to work for you. Okay, so basically for the remainder of this lecture, what we're going to do is actually try to do exactly that. We're going to, first of all, talk about the Fourier transformation, just to make sure that we are all in the same page, how to do Fourier transformation of a signal. And after that, it's basically almost trivial. Basically, make the point that you don't like as 0, the particular frequencies you don't like, put them as 0. And the frequencies you like, you put them as 1. And that's it. Just keep them the same way they are. Okay? Would you like to continue or would you like to have a break first before we go into the frequency domain? It's up to you, really. I'm fine both ways. Continue or break?
Maybe let's continue.
Okay. Are the other guys okay with that?
Okay, Doctor.
Okay. So now we're going to talk about the Fourier transformation. Of course, what we're talking about here, since we're talking about a signal in a computer, so we're talking about a discrete signal. Actually, it's not just discrete. We should actually call it digital signal. Digital signal meaning that it is sampled and quantized. The sampling is basically, I'm not taking all the points, I'm taking only points at T sampling, twice T sampling, and so on. Quantized meaning that the amplitude basically is not represented as a real number, it just has a certain quantization, like you represent the amplitude as a 16-bit number, for example. Okay. In this case, when we talk about digital signals, we are going to use something called the discrete Fourier transformation. Okay, or DFT. The DFT has a very popular version called FFT, fast Fourier transformation. Basically, they are exactly the same. Same output, exactly, okay? The difference between them is the processing time. The FFT is more efficient. In MATLAB, they used to have two functions. One is DFT and one is FFT. Right now, they removed the DFT. So if you try to use DFT, let me try it just to show you how it works. Maybe I'll just generate a signal, x is equal 1 to 128, just any signal, okay? And I say, for example, xf is equal to DFT of x. Okay, basically, it told me that unrecognized function or variable DFT, do you mean FFT? Basically, now they replace DFT with FFT. So basically, FFT is the discrete Fourier transformation in MATLAB. Okay, now we have samples in and samples out. So let's try it with that. Basically, we're going to try it exactly like that. XF is equal to, let's have a few points. X is equal to from 1 to 10. Okay, and I'm going to have FFT of Fx is equal to FFT of x. Here, I used 10 points at the input. I got 10 points at the output. How do you relate the points in the output here to the frequency that you know? Basically, you have samples here. You have 6 samples. Basically, it's an array of 10 values. What are their frequencies? We need to know that. So basically, here we're going to talk about that in this part. So basically, what you have at the input, let's draw everything in some detail. Just have a signal that looks like this, okay? Imagine that you have a signal like this, okay? This is 0.01234, okay? And you got signal at the output that looks like this, exactly the same way. Basically, you have here 5 points. You're going to end up having 5 points at the other end. Okay. How do you relate these to those? Okay. First of all, let's talk about if you have a generic signal. Basically, you start from here. This is the start, this is the end. And you got a spectrum here. This is the start, this is the end. Okay. basically we have to define here basically periods here, and you have here also periods because it's sampled. It's sampled on both. So let's call this part here sample period TS, and you have endpoints. This is sample number 1, this is NS, number of samples. So the total duration here, duration is what? Duration of the signal is, let's just call it capital T. This duration here is capital T is equal to NS TS, number of samples times TS. This is the duration of your signal. Here, let's call this DF, and let's call the whole thing here bandwidth. Please don't confuse it with baseline one, this is bandwidth, okay? Maybe you can just use another term because actually this can be very confusing. So basically, let's call it capital F, okay? So it's like this here. There is a relationship between, basically, this. There is a relationship between DF and T, and another relationship between TS and F. And it's an inverse relationship. Let's start with this one here. F here is by definition equals to 1 over. In the other one here, you have DF is equal to 1 over T. So it's an inverse relationship between the two. This is the resolution here, and this is the sampling period here, and this is the resolution in the frequency domain. This is the bandwidth in the frequency domain. Let me just write it so that you can remember it, okay? And this is basically the duration of your signal. So basically, I need, first of all, if I have a signal like this, I have to give TS. How much is TS? Let's just say TS is equal to 1 second. So the duration here is from 0 to 4. It's what? It's basically, actually, this actually should be NTS, so basically it's 5. Between 0 and 4. Here you're going to have this distance right there is DF. It's going to be what? 1 over 5 hertz. Notice the units, because basically you have 1 over time, so it's hertz. How about the bandwidth? It's basically 1 over TS, which is going to be 1 hertz. Okay. MATLAB does basically, first of all, in the assumptions of the discrete Fourier transformation, they assume that whatever is in here and in here is just a periodic extension of this. So basically, they assume, because they have to do an assumption actually in order to get a sample Fourier domain. So they assume that you have exactly the same pattern here and the same pattern here, and it's repetitive. So basically, you're assuming that whatever you're giving the computer is just one period of a periodic signal. And also, the result will be basically one period of a periodic signal. Okay? So in MATLAB, what happens is that it gives you something that would look a little bit strange. Okay? Let's, first of all, do you remember the Fourier transformation from your signal and system? If I have a signal that looks like a gate, and take the Fourier transformation, do you remember how it looks like here in the frequency domain? This is x of t. I want to know how x of f or x of omega looks like. If you remember, it looks like a sinc function. Remember that? Do you remember that? Okay. So basically, I'm telling you about this because actually what I'm going to do now is I'm going to try that in MATLAB and see what comes out. Okay, so let's try and have a signal that looks like this and try to use FFT and see what comes out. So let's start another code here and call it lecture 3 code. Okay. So basically I'm going to generate a signal that looks like this. Let's just have zeros of 128 and 1, a length 128, and I'm going to have x of from 1 to 8 equal to, or from 16 and 1 to 8, it's fine, is equal to 1. Okay. So basically this should look like a gate. Should look like something like what we saw just a few seconds ago. I have a figure. I'm just going to draw that. Subplot. That should close all. Subplot 2, 1, 1. Okay, for the 3, 1, 1. Plot of x. And then I'm going to have frequency domain fx is equal to FFT of x. Okay? And the FFT is usually complex. So basically, I'm going to draw the magnitude of the Fourier transformation. So here I'm going to say absolute of fx, absolute basically the magnitude. Okay, let's look at what comes out. How do you like that? Does this look like a sinc function? Actually, it's a little bit strange actually, because in MATLAB, it starts from 0, frequency 0. If you go back to what we were talking about now, basically this is out of the, this is supposed to be the spectrum of the gate function. The 0 is here in the middle, so the peak here is at 0. MATLAB basically starts from 0 and on, and basically it gives you a limited amount, because actually we're talking about a discrete value. So basically what you have is something that looks like this. Basically you start from here, you start from here and basically end to here, and basically there is another one like this here. So you take it and basically what you see is something from here to here, from the 0 of the first one to the 0 of the second one, because it's actually endpoints. So what you see here is basically this is the shape from the first copy of the frequency domain, and this is basically the first part of the second copy, because actually it's periodic in the frequency domain. It might be confusing, but actually they have in MATLAB a very nice way of showing you the Fourier domain the way you like it. Okay, basically there's a function called FFT shifts. Okay, so basically here if I put FFT shifts, what it does is basically makes the 0 in the middle. So basically I'm going to draw that here. How do you like that now? The last one here looks like what we'd expect to have from a Fourier transformation, regular Fourier transformation, where the 0 is in the middle. Okay, so whenever I wanted to have the frequency domain the way I like it, the way I know how to deal with it, I have to put an FFT shift. If I put an FFT shift, what I will have is basically something that looks like this. The 0 will be in the middle. So if I have, for example, 128 points, the 0 will be at 128 over 64 over 2 plus 1. Because basically it has n over 2 points, then the 0, and then n over 2 minus 1 points. Okay, So if I have 128 points, the zero will be at 65. If I have 1,000 points, the zero will be at 501. So basically now I know how to compute the frequency domain. If I wanted, for example, to remove a particular frequency, all I have to do is just basically remove the frequency I don't like. Just go and basically make it zero. Very simple. So for example, if I decided to remove the DC value, I can go and at 0.65 and make it zero. That's it. Okay. If I wanted to have a range equal to zero, that's fine. I can do that as well. So what we're going to do now is do exactly that for our ECG signal. We already have the baseline wonder, and we computed, or basically we knew that the artifact is below 1 Hertz. So let's go and basically remove all the frequencies between 1 Hertz and -1. Basically, this is supposed to be like 0, this is minus, this is plus. So I'm just going to remove the center part that corresponds to the negative and positive frequencies of the cutoff frequencies that I want. So basically what I plan to do is to do something that is exactly like what I was saying here. Okay? Let's first start with basically just looking at the frequency domain. What we did in the ECG demo, remember the code that we basically, it was basically what we have in the in the original code that I gave to you. Maybe I should start with another one. ECG demo. Okay. Okay. This is the ECG demo code that we used to produce the 60 Hertz, if you remember. Okay, let me put the magnitude of the artifact a little bit small. It was here 1 over SNR, signal to noise ratio. No, I should just put that as 8. The N times this. Equals to 50. Okay. It's not exactly, this is actually, okay, I actually here I normalize the signal. I shouldn't have done that. I don't want to do that here. This is basically what we had last time. We just added 60 Hertz on top of the basically the original signal. Let's do something that would basically take both these signals and display their spectrum. So I want to have another figure where I see the frequency domain of this and the frequency domain of that, and basically I can also take the difference and see how it looks like. So what I'm going to do, basically, this is exactly the frequency domain, the ECG demo code, where I just load the signals. I need only one of them. And basically what I'm going to do now is basically I'm going to compute the frequency domain of sig and fsig and sig noise. So fsig is equal to FFT shift of FFT of sig. If I wanted to put the magnitude so that I can display it right away, I can put it here. Okay. I'm going to have this frequency domain of A sig n, and let's just move the absolute so that we can actually go back. Okay, so I'm going to have another figure. Of T11 and plot the absolute value of fsig. and exceed n. Let's see how that looks like. And maybe I can get the difference also. Whether only one. This should be at 1, at 3. So when we do that, okay, okay. See how that looks like? This is basically the original, and this is the one with the noise. And here I can't really see any frequency, but actually it shouldn't be 0. Let me just check. If sig n minus f sig n. Oh, okay, here I should have f sig n, not sig. See now? Now you see the spectrum of the artifact, the spectrum of the noise very clearly from here. Remember when we were talking about the estimation of the artifact, we were talking about estimating that from the actual signal using estimates of the frequency, whether it's lower or higher than the original signal, things of that sort. Here in the frequency domain, it pops up like this. Looks very clear, actually. Very clearly, you have the artifact at this particular frequency, here, and here. So all you have to do is just zero out these two. Just make these as 0, basically, okay? It's very simple, okay? If you do that, basically you're gonna end up with a completely clean signal, okay? Let's do exactly the same thing for, basically just save that into, instead of 60 Hertz, just use the baseline wonder. Okay, so here instead of having the noisy signal as the simulated signal, I'm going to have the noisy signal as the baseline wonder. Remember that from here, basically the data that you have here, it's for example S118, BW12, this is the one that has the baseline wonder signal. So I'm going to use that. So basically I'm just gonna do that here, basically sig n, or sig, this is the original one. I'm gonna have sig n equal to S118 BW12 of the same range, just have the same exact signal. Let's see that, and basically, of course, the other, we should just remove that so that we don't have confusion. Okay, let's leave it for now, because actually these are, just correct that, BW noise. See here, first of all, the figure 1 here, you see the same artifact here. Now you see the difference between these two. It looks something like this. It looks very clearly in the part where there is low frequency. Maybe we can magnify it a little bit. See now? It's clear that it's very low frequency. Okay? In order for us to see that again in another signal, maybe you can just use here, instead of using the BW, we just use EMG, MA. You know, the difference between the two, the one with the artifact and the original signal, actually, it has components in the high frequency range, not just in the low frequency. So actually, for the baseline wonder, it looked very clearly in the middle range. So in order for us to demonstrate the idea about how to zero the filter, how to zero or basically remove the frequency that correspond to the artifact, okay? Sorry. what we're going to do here is just basically taking the f sig n and making the parts that we are not interested in and just making them all equal to 0. Okay, so basically this is frequency domain filtering. Okay, so first of all we have to define the parameters that we talked about in the lecture. df is equal to what? Basically from what we had here, df is equal to 1 over t, capital T. T is n times ts. The f, the bandwidth, is equal to 1 over ts. So basically, we're going to do that here in the code. df is equal to 1 over the number of samples here. I think I have a value for it. Let's define it as npts. And ns, okay, is equal to 10,000. And basically, I'm just going to put the range here so that it can be flexible if you change ns. So now the ns is equal to that. So basically 1 over ns and times ts. Okay, and capital F is equal to 1 over ts. Okay, so basically just to give you another hint about the Fourier transformation. Basically, the bandwidth here is equal to the sampling frequency. Basically, because it's 1 over ts, this is the sampling frequency. The bandwidth is equal to the sampling frequency. It's from minus to plus, meaning that it's from f over 2 to f over 2, which means that basically it's the f sampling over 2 minus f sampling over 2 to f sampling over 2. That's why we say that if you have a frequency above the sampling frequency over 2, you're going to be aliased. You're going to have like improper sampling. So you have to make sure that all the interesting frequencies that you have, or basically all the frequencies in the signal, are below f sampling over 2. Or in other words, in a Nyquist-Syrian, the frequency sampling should be twice the maximum frequency of the signal. Okay, so this is just a reminder of the Nyquist frequency. Now, the cutoff frequency we were talking about, let's say the cutoff frequency is 1 Hertz. Okay, and of course the values here we're going to have are also in Hertz. This is in Hertz, this is in Hertz. Okay, so basically, how many points should I remove? If I wanted to remove all frequencies below 1 Hertz, how many points should I remove? Can you answer? How many points in the spectrum?
1 Hertz, Doctor.
In Hertz, no, how many points in number of points? You have 1 Hertz. How many points in the spectrum within 1 Hertz? Basically, df is the sampling of the frequency domain. Basically here, this is a sampling, this is a step. So if I have 1 Hertz, for example, this much, then if you divide it by df, it's going to give you how many samples you need to remove within that 1 Hertz. Again, the step here in the frequency domain between the samples is df. If I have a frequency like 10 Hertz, I wanted to know how many points are within 10 Hertz. What should I do? I divide 10 Hertz over df. So basically, this will give me exactly how many points I should remove. So basically, what we are going to do now, first of all, we assume that the 0 point is at what? At ns over 2. So I'm going to take f sig n and start from ns over 2, okay, plus 1, okay, which is basically the allocation of the 0, the DC value, and start from FC over DF. Basically, this is the number of points I should remove to basically remove all the frequencies basically within a 1 Hertz range. So I start from that and end in the same thing. Okay, plus. So basically, this is a middle point here. I take from minus FC over DF to plus FC over DF. Okay, and make all that equal to 0. That's it. This is a filter. Okay. There is one very important point is that if you are basically taking or indexing an array, you cannot have a fraction. So this can be a fraction. Okay, so I don't want to have a fraction. So basically, I have to round that, so that it becomes an integer. So basically, round that and round that. Okay. In order for us to see whether this is working or not, what I'm going to do now is I'm going to repeat this here. Maybe I should have another figure here. And basically, I'm going to plot the difference between the new one here, f sig n, f sin n, f sig n, the new one after the removal, okay, minus f sig. Okay, so that I can basically determine what actually happened, whether actually I removed the part I wanted or not. Okay, so let's look at that. But there is an important point also here, because basically we're going to remove the DC value. We have to add it again. Okay, so basically what I'm going to do is the DC value is usually the maximum value in your spectrum. So basically I'm going to estimate that and add it to the signal. Or I can basically, actually it's fine, it's fine. I don't need to do that. Maybe just plot it and see if it makes a difference or not. Oh, okay, I'm sorry, and I'm still working with the BW12. Okay. Actually, the magnitude here is much smaller. There's something wrong here. Okay, the DC value here is making a problem. So let's remove the DC value or what? I'm not sure why that looks like this, but actually, let's continue till the end and then see what this looks like. So basically, assuming that we did that right here, what we're going to do is basically in order for us to get the actual signal, I'm going to take f sig or sig f, sig n filters will be basically IFFT of FFT shifts of the f sig n. The way I'm using here FFT shift is because basically I use FFT shifts to get f sig, and in order to use IFFT, I need to return it back to the way it was. FFT shift, if you apply it twice, it basically returns back the signal to the original way. Okay, so if I do that, so sig f, sig nf is a filtered version of sig n. What I'm going to do is basically estimate the DC value first of the sig n, which is basically the mean value of sig n. And basically, before I display it here, let's just draw it in a new figure. I'm going to basically add the DC value. So basically, I'm going to have basically plots of the real part, basically I take the real part or the absolute value, it should be the same. The real part of sig n f plus bc, okay, and see how it looks like. How do you like that? Does it look nice? Let's draw the other one on top of it. Let's do exactly what we did before. Plot sig n and hold on, and then plot this and hold off. We should have that in red. How do you like that? Let's magnify also a part. Maybe the same part that we looked at before, the other one. How do you like that?
Much.
Looks nice. Basically, it has everything. It has basically the same results as the one you got from filt. All we did basically was just go and remove a few points. This is basically, see the code here. This is a step when we did the filtering. If I remove this, let's remove this. Okay, you're not going to see anything. Basically, it's going to come out exactly the same. So it's just one step. I made some points equal to 0. That's it. So this is an ideal filter. Okay, so an ideal frequency domain filter looks like this. Basically, it just gives me exactly. Basically, I zero in. I basically zero out the points that I don't want in the frequency domain. I leave the others, and that's it. Okay, let me try something a little bit different, so that you can basically see that this is actually very effective. Basically, what I'm going to do is I'm going to have this part, if sig. Actually, I wanted to do it the opposite way. So basically, if I have this, let's just say that, let's have another one, another signal with the same name. 1 is equal to sig n, and I'm going to zero out that. And then I'm going to subtract these two. So f sig n is equal to f sig n minus f sig n1. What do you expect that to do? Now this is a filter I used to have. Okay. Now I have basically I subtracted the filter, the one that I did here from the original one. What do you expect the output to be? Okay, let's see it. How do you like that? Basically, I subtracted the original one from another with the artifact removed. So basically, everything will be removed except the artifact. Okay, so now I changed the filter from a low pass filter to a high pass filter, or from a high pass filter into a low pass filter. So now I kept all the components that are below 1 Hertz. Okay, let me draw it for you in order for you to imagine it a little bit better. Basically, I had a component that looks like, basically the original component had all frequencies. Okay, like this. Okay, what I did was to zero a part of it. So it came out like this. Then I subtracted these two. It will become like what? Basically, this will remove this, and basically this will remain. So basically, you're gonna come up with something that looks like this. So instead of having here, this is high pass filter, you came up with something that looks like a low pass filter here. So in order for you to implement a low pass filter using frequency domain, it's very easy. You do the same thing. If you have the cutoff frequency, you can do it exactly the same way you did it for the high-pass filter, but basically subtract the output from that, from the original one. Okay? Is it clear?
Yes, doctor.
Okay. I think I'm going to stop right now, stop here. And basically the part about the frequency domain filters, we're going to review again in the next lecture. I'm going to give you a question about it in the assignment, but don't worry about it, okay? If you did it wrong, and basically you don't have to do it right from the first time, because the deadline for the submission will be after the next lecture, so that if you have something that you're not sure of, you're probably going to have 2 days after the lecture, next lecture, so that you can submit this part right. Okay? So as we said, what we're going to do is basically give an assignment about the baseline wonder using all kinds of things that we saw here. The goal of this assignment is to make sure that you're catching up with whatever we had so far. Okay? And basically, for just as a reminder, next Friday, we don't have a lecture next Friday.
Okay, doctor. If you don't mind, doctor, I have doubt.
You have what?
I have question, please.
Go ahead, go ahead.
Okay, about the assignment deadline at, I think, 26th of September.
No, this is, don't worry about it. No, don't worry about this. What we're going to do next, we have another deadline now that will be basically after the following lecture. So basically next time, today is 18, right? Let me get the, basically next time is going to be the 25th. The next lecture will be actually October 2nd. The next deadline for your work will be basically on the 4th of October. Okay? The other one, the 26th, that was supposed to be for research problem 1, will be pushed back to basically a couple of weeks from this one here. So basically, instead of 4 here, you're going to have on the 18th or something like that. So don't worry about the deadlines.
Okay, thank you very much.
So basically, from now till our next lecture on October 2nd, please feel free to contact me anytime if you have any questions. You can send me an email, you can send me a WhatsApp or whatever, and you can also communicate with your colleagues. But the most important thing is basically understand the topics in the assignment, understand the topics that we covered so far, so that we can build on them in the following lectures. Basically, if you have any questions, let me know and we can explain them again. The deadlines of the assignments, we are in a graduate course. Don't worry about the deadlines. If you have reasonable questions, if you have things that you don't understand, I'm going to allow you to basically submit your homework or your assignment late. It's fine, okay? It's the most important thing is not meeting the deadlines. It's basically understanding the material. Okay?
Okay, thank you, doctor.
Okay. Any question? Any more questions?
Thank you, doctor.
Thank you very much.
Okay. Okay. So inshallah, I'll see you in 2 weeks, inshallah. And have a happy National Day, inshallah.
Thank you very much. Don't forget the recording.
The what?
The recording for this lecture. Submit.
Actually, it's going to be available like every other time, basically, in maybe by tomorrow morning. Usually, they say that it's 6 hours after the recording is done. It is available on Blackboard. So it should be available, inshallah, tomorrow morning.
Thank you very much.
Okay. Good luck, inshallah. And see you, inshallah, in a couple of weeks.
Thank you.
Assalamu alaikum.
Alaikum salam.